Weak acid titrations. So neutralization reaction is when an acid and base react and they're going to produce water and often a salt or some other compound anyways. The equivalence point is when an equal amount of the hydrogen ions, or when they're attached to water hydronium ions, and hydroxide ions have reacted. Now, this isn't necessarily at a pH of 7, and we're going to look at why that is with a weak acid titration. So strong acid-base titration, you have a strong acid reacting with a strong base, and they are going to come to an equivalence point of 7. This is as long as both of them are strong, and so the other parts, essentially the salt that is formed, those ions do not change the pH, and so it is going to stay at 7. These are pretty easy to do. It's essentially just a limiting reactant question to see which one there's more of. Is there going to be more hydrogen or more hydroxide? As long as they're equal, you'll get a pH of 7. If there's more of one than the other, then there'll be a certain amount of hydrogen ions left over or a certain amount of hydroxide ions left over, and then you can use that to find the pH. With a weak acid strong base titration, the weak acid itself is going to react with the strong base, and so the hydrogens from the weak acid and the hydroxides from the base are going to react and neutralize. So we still do have that neutralization, but there is going to be some left over. So the anion that was the other part of the acid. So if we had our weak acid with a generic formula of a hydrogen and an anion, this hydrogen is going to neutralize the hydroxide and take care of itself, but this anion will be left over. And we know it is the conjugate partner, because in the reaction it would let go of the hydrogen and have this anion here. This is a conjugate partner of the acid, and we know that it is a conjugate base. And so essentially we're going to end up setting up a new equilibrium between this anion that gets produced, and if there is any weak acid left over, we're going to get an equilibrium system between the two, which we can then find the pH of. So we have to factor in all of the species that are there, so we'll keep track of them as we go through there. Often we're going to be finding the pH either before the equivalence is reached, so when there's still some of this weak acid left over, or at the equivalence point once we've used up all of this weak acid. Just to compare that to a strong acid with a weak base, in this case the opposite is going to be true, is that we're going to have a weak base and it's going to produce a conjugate partner that is going to be an acid, and so that acid is going to end up making sure that the pH at equivalence point ends up being below 7 in that case. We won't be looking at that calculation today. All right, so for a weak acid and a strong base titration, and specifically we're going to be looking at before the equivalence point. So we haven't added in enough of this base to fully neutralize the weak acid. So we have, in this particular question here, we have a 15 milliliters of a 0.25 mole per liter solution of weak base. So this is the base that we're using here and the amount that we have. Then the acid that we're using is 25.2, and it is a 0.3 molar solution of acid. And just based on those numbers, we can see that the acid's more concentrated and there's more of it. So there won't be enough base to fully neutralize that acid. So that's one thing to note. We know that this is going to be before equivalence point. We'll do the math just to make sure. We're also given the Ka of the acid as well. So when we go to do our equilibrium expression, we have that Ka to work with. Visualizing this, again, we would be taking the base and we'd be adding that into the base, and we'd be adding that into our acid. And so it's a good idea to sort of visualize, okay, how much acid do we have, how much base do we have, and what are the reactions going to be as we go through this. So let's break it up into steps. First thing is that when we're adding this base into the acid, we've got a bunch of things to keep track of, so we should note as to what they are. So the sodium hydroxide is going to become in the form of sodium ions and hydroxide ions. There's going to be water sitting in both with the base and with the acid, and then the acid itself has this weak acid, ASA, and it's sitting as a molecule before it has dissociated. We know that it will dissociate on its own, but what's going to happen is that the base is going to cause it to dissociate more than it wants to. And we got to figure out how much that is going to be. So to do that, let's consider the NaOH is going to be completely ionized and completely dissolved, And so if we have 0.25 moles per liter of NaOH, then it's a 1-to-1 ratio. So we must also have 0.25 moles per liter of the OH ions as well. The N plus ion, we know this is a salt ion. It's not going to affect water, it's not going to hydrolyze water in any way, so it's not going to change the pH. So really, it's there. We could find out how much we wanted if we wanted to, but it's not going to affect the pH, so we're just going to ignore it. So the OHs are going to start taking the H's from the acid. So the acid is going to be sitting there, and it'll establish an equilibrium where it lets go of some of its hydrogen ions, but not all of them because it's a weak acid. So it'll let go of some of them. But then the OHs come around and they start stealing these H's. And what that's going to do is it's going to shift the reaction, just as Le Chatelier's principle says. It'll shift the reaction to the right to replace them. And so this HA is going to dissociate more than it would on its own because the OHs keep taking the hydrogen ions that dissociate it. So think of the base is essentially bullying the HA into dissociating more than it wants to do. We need to figure out to what extent that is. And it is based on how much base we have. So the question said that we have 15 milliliters, or 0.015 liters. This is in moles per liter, so put the volume in liters as well. So if we actually find the number of moles of OH, we know how much OHs are going to be there taking these hydrogen ions. And it works out to be 0.00375 moles of OH. That's how much has been added in given this question. And just to make it easier to write, so we don't have to do scientific notation or write all those zeros, let's use millimoles. So 3.75 millimoles of OH have been added into the acid. So if there's 3.75 millimoles of HA that have to react with this OH. So if you think of this HA, we had a bunch of it to start with. We've added in 3.75 millimoles of this OH, and so they're essentially going to be subtracting 3.75 millimoles of the acid in order to neutralize. So those hydrogen ions from the acid will react with the OH ions, and they're going to form water. That's our neutralization. So whatever amount of OHs we add in, that's how many hydrogen ions have to be taken away from our weak acid. Now, we need to realize that every hydrogen ion we make, remember we also make the anion of the weak acid as well. So if your OH is forcing 3.75 of the millimoles of the hydrogen ions to be produced from the weak acid, then that same amount of anions is also going to be produced, because remember, as the HA dissociates, for every one hydrogen ion you get, you're also going to get one anion. So if 3.75 of these guys have to be made, 3.75 of the anions also get made. So we're going to have 3.75 millimoles of those anions floating around, plus whatever's left over of our weak acid. The OHs, they're going to neutralize with the H's, so it'll be gone. The water we don't care about, but the anion and the leftover weak acid we do care about. We've got to figure out what those amounts are. So now we have none of the OH, because again, the H from the acid has been used to neutralize those. The Na ions that came with the OHs, then the sodium hydroxide, we don't care about. They don't affect pH. We got water in there. That's not going to change the pH. The leftover acid, so we started off with a certain amount. We used up 3.75 millimoles of it, but we still have some left over, so we got to figure out what that is, because that's going to come to an equilibrium and affect the pH. And the amount of anions that we have made while dissociating the weak acid, we've got to figure out how many anions we produced, and again, figure out how the equilibrium is going to work with those guys. So we have to find essentially the concentration of the acid left over and of the anion produced when this sodium hydroxide was being neutralized. So we're going to have some leftover weak acid, some anion that's produced. They're going to come to a new equilibrium, and that'll affect the pH. We need to figure out how much we have of each of these ones, and then we can throw them into an ice table and find out the pH of the resulting solution. So to find those initial concentrations, let's find out how much we have. So again, originally the total amount of weak acid that we had was the concentration times the volume. So we had the concentration was 0.300 moles per liter, and there was 25.2 milliliters of it, or 0.0252 liters. So that means that originally we had 0.00756 moles of this weak acid, or without all the zeros, 7.56 millimoles of the weak acid. We know we used up 3.75 in order to, and I wrote the OH here, so this is where the number is coming from. That's how much sodium hydroxide was added. So that's how much of the weak acid has to be used to neutralize the sodium hydroxide. So the initial amount of weak acid minus the amount that was used to neutralize the OH is going to give us a leftover amount of weak acid of 3.81 millimoles. Note that if these two numbers were equal, if the amount of base we added was equal to the amount of acid we have, that would put us at the equivalence point. For this particular part of the question, we are before the equivalence point, so there's less of the base being added, and there's going to be some leftover weak acid. Realize the volume's changing as well, because we had the 25 milliliters of the acid, we added in the 15 milliliters, so we end up with a total of 40.2 milliliters. We have the amount in moles, we now have the volume, so we can use that to do our concentrations. The acid that was left over, 3.81 millimoles, divide by the volume, and if this is in millimoles and that is in milliliters, the milli cancels out, and we are in moles per liter. Let the metric system do its work for you. So our concentration of our weak acid is 0.09478 moles per liter. We need to do the same thing for the anion. It's number of moles divided by the now new total volume. So this is, again, these guys are sitting together in that solution. There is 3.75 millimoles of this anion here. So its concentration is going to be 0.09328 moles per liter of the anion. So now I have my two entities. I've got my leftover weak acid, and I have my anion that got produced by the neutralization with the base. If I consider them in a equilibrium system, my weak acid and my anion are going to establish an equilibrium, and there's going to be a certain amount of hydrogen ions involved in that process. So if I put in the initial concentration of HA, so that amount that was left over after that neutralization happened with the OH, the amount of anion that got produced in that process, there then, so this is my ICE table here, just to keep track of the points in time. So these are the initial concentrations before the equilibrium happens. So you can think of these as happening sort of in two phases. There's the first phase that we just did in terms of getting the neutralization done and working out what the numbers will be. Then there is the getting to equilibrium that is going to happen between whatever's left over. So we know that we have 0 hydrogens here initially, because again the hydroxide had neutralized with the ones that we did produce, so they're gone. So initially that's going to be 0. So we know we're going to have a shift to the right, because you can't go down from 0. And so we are going to be going up in our products, and we're going to be going down in our reactants. So we have our equilibrium concentrations here, and this is set up for a weak acid. So we can write our equilibrium expression, products over reactants, use the Ka given to us in the question, plug the numbers in, the reactants over the products, and so we can check the 100 rule to see if the X that we're subtracting out is going to be significantly smaller by taking the concentration that we're going to be subtracting it from and dividing by the equilibrium constant. It doesn't end up being over 100, so it is quite close, which means the X isn't going to be significantly smaller. So we can't subtract it out away from either, and these numbers are pretty close, but these X's here we can't ignore. They're going to be relatively large compared to the numbers in which we're using them. So we have to actually do the math, expand out the brackets, and we're going to end up having to do a quadratic. So we have the equation set equal to 0, run it through the quadratic, and realize that the negative value is not going to work because this is the concentration of hydrogen. So we should end up with a 0.001063 as our concentration of hydrogen, which when we take the negative log of that, we will have our pH. So once this sodium hydroxide has been added in the particular amounts that it is there, we end up with a pH of 2.973. And this is, again, we're not at the equivalence point yet. This is before the equivalence point. We've added in a certain amount of base, and it has given us a particular pH value. Now let's try doing it at the equivalence point. So we'll do the same situation, the same acid, but if we kept adding in base until we got to the equivalence point. So the acid itself has not changed. We're using the same base with the same concentration, but this question, as with many of them, they're telling you it's at the equivalence point, but they're not saying how many milliliters or what volume of NaOH has been added to get to that equivalence point. One thing to note, we'll see this later here, remember the relationship between conjugate partners. If it is not just a matter of reversing the equation and taking the inverse of the K value, that doesn't work with conjugate partners. And we'll see that a little bit later when we actually look at this equilibrium once we figured out the neutralization part. All right, so at the equivalence point, the amount of hydroxide ions that's coming from the sodium hydroxide is going to equal the amount of hydrogen ions that come from the weak acid. So essentially, however much weak acid there are, you'll get a certain amount of hydrogen ions, and we'll need an equal amount of hydroxide ions that comes from the base to get those to be at the equivalence point. So the hydroxide and the hydrogen ions have to equal each other. So if we find out how much acid we have, then we'll know how much hydroxide we would need to get it to the equivalence point. So our acid itself is 0.3 moles per liter, and we have 25.2 milliliters. So that gives a total of 7.56 millimoles of the acid. So to get to the equivalence point, we need 7.5 millimoles of hydroxide. So that's the amount that we need. But remember, it's coming in a solution, so we're going to have to figure out what the volume is. So calculate the volume of the sodium hydroxide needed. Just do a volume calculation. So if we take our millimoles and we divide by 0.25 moles per liter, again, the moles are going to cancel out and we're going to end up with milliliters. So we're going to have to add 30.24 milliliters of sodium hydroxide in order to get the same number of millimoles of OH as the weak acid has, which is 7.56. So 30.24 milliliters of NaOH will end up putting 7.56 millimoles of NaOH into the solution, which is the same amount as the weak acid that is in solution. So we have to get those to be equal. Doing so, we're going to be putting the two volumes together. So we're going to end up with a new total volume because we're going to have to figure out concentrations. So the new total volume of the solution ends up being 55.44 milliliters. All of those millimoles of the weak acid are going to have to dissociate. And that seems counterintuitive because you say, okay, well, the thing about weak acids is they don't fully dissociate. But again, the OH is going to force them to dissociate. So for every hydrogen, so again, the weak acid doesn't want to fully dissociate under normal conditions. If it's just hanging out in water, it's not going to fully dissociate. But let's say it did produce one hydrogen ion, and if there's a hydroxide that was around from the base, it's going to grab onto that hydrogen ion and turn it into water, and it'll be gone. So then the acid would produce another one, and then a hydroxide, if it's there, would take it too, and it would be gone. And so the acid would have to produce another one, and that one would get taken as well. And so this is essentially going to have to shift all the way to the right as long as there's hydroxide. And remember, we put the exact amount of hydroxide that it would take to do this, to completely dissociate that weak acid. So yes, weak acids don't want to fully dissociate on their own, but a hydroxide can bully them into doing it. And in doing so, we end up with zero of that weak acid left over because it's all dissociated by the hydroxide. The hydroxide reacted with the H plus, so they made water, so they're all gone as well. The water's there, but we don't care about it. And what we do need to realize is for every HA that did dissociate, we got another anion. And so if we dissociated 7.56 millimoles of HA, we would have produced 7.56 millimoles of anion. So now what we have is the OHs from the base that we added in, they completely neutralized with the hydrogen, so they're gone. The hydrogens, that same reason, they're gone because they neutralized with the OH, so those two things are gone. The sodium and the water don't affect the pH, so we don't care about them. They're there. We don't worry about them. Realize the HA again is gone because we added enough base to make sure that it was completely dissociated, so it's no longer there. So the only thing that we now have are these anions that got produced by the dissociation. And remember, this is the conjugate partner of a weak acid, which is a conjugate base. And the conjugate base will affect the pH. So we're going to find the initial concentration of the relevant species. In this case, it is only the anion. We're going to put that into an ice table, and we're going to solve for pH. Now remember, this is a conjugate base. So the new volume, 55.44. So when we go to find the concentration, we don't need to worry about the weak acid because it's gone. But the concentration of the anion is the amount that we have divided by the new volume. So we have 0.1364 moles per liter of anion. And remember, this is a base. So when we go to write our equation, we're not talking about a weak acid anymore because we don't have any weak acid. We have a weak base. So we're going to set up our equilibrium equation for a weak base acting on water and look at the OH concentration as that happens. So there's our equation. Our base reacting with our water is going to be picking up the hydrogen ions, and it is going to be producing these hydroxide ions. Remember, water's concentration is going to remain constant, so we can just ignore that column. We put in the amount of base that we start with. It's going to be changing by some amount. And remember, it is going to be shifting to the right because, again, there's no products there. There's no OHs because they all reacted, all the ones from the sodium hydroxide reacted with the weak acid, so it's gone. This here, which is essentially our weak acid, there's also none of it as well, the conjugate partner. So we have our base going down by X, and then we have X and X amount of our product. So realize, and again, don't forget this is a base, so we are using Kb. The question gave us our Ka, and we know that Ka and Kb, as long as they are conjugate partners, their multiple is going to be Kw. So you know what Kw is, it's 1 times 10 to the negative 14. You know what Ka is because the question gave it to you. So we can solve for Kb, and we can plug that into our equilibrium expression. Now, a quick thing with X here. We were talking about ignoring it earlier. Again, we can do the math and we can say, okay, look, can we check to see whether we can ignore this? Looking at this Kb, we definitely can ignore it because if you take our 0.1364 and we divide by our Kb, 9.35 times 10 to the negative 12, you probably don't need a calculator to realize that that's going to work out to be much over 100. So that means that that X right there relative to 0.1364 is pretty small, so we could ignore it. I'll leave it in just for fun. If you do ignore it, makes your calculations a little bit easier, so feel free to ignore that X and solve for X. Either way, you will end up with an X value. You could avoid the quadratic, but you'll end up with a X value, a negative one that you can ignore, and an X value of 1.13 times 10 to the negative 6. Now, don't just take the negative log of it and say, okay, that's the pH, because this is the OH concentration, because that's how we set up our ice table. X is equal to the OH concentration. So taking the negative log of it will give you the POH, which is fine, but if the question asks for the pH, make sure you then translate it into a pH of 8.05.